Today we will discuss Unit 18, certain forms of convergence. Unit 18. Unit 18. Certain forms of convergence. Certain forms of certain forms of convergence. Certain forms of convergence. Concepts. Concept means definitions or formulas. Concept. Contents, aims and objectives, introduction, convergence in measure, convergence in mean, almost uniform convergence, summary solutions of a series, aims and objectives, introduction. Suppose Fn is a sequence of real valued function defined on a set E, which is a subset of metric space. We call Fn is said to be convergence pointwise on E. Okay, so a sequence Fn uh, is Fn of a function defined on E is said to be convergence uniformly to F. Convergence uniformly to F on E is said to be convergence for positive. The sequence definition, 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 definition. The sequence Fn is of a function. The sequence sequence Fn. The sequence Fn. The sequence Fn of functions defined on of functions. FNS means functions defined on E. Defined on E. Is said to be convergence. Is said to be. Is said to be convergence. Is said to be convergence. Is said to be convergence. Pointwise enough. Pointwise on F. F. Epsilon greater than 0. Next. A function Fn of a function. A sequence. A sequence. Sequence. Fn. Sequence Fn of functions defined on NS means functions defined on defined on functions defined on functions defined on functions defined on E is said to be convergence is said to be said to be convergence. Said to be convergence. Is said to be convergence. Uniformly, uniformly to F. Yes, uniformly, uniformly to F. Uniformly. So, yeah, definition one. Almost uniform convergence. Definition one. Definition. Definition one. Let Fn be a sequence of measurable functions. Definition one. Let Fn be a sequence of measurable functions. Fn be a sequence of measurable functions. Yeah. sequence of measurable functions. FNS means measurable functions. Sequence of measurable functions. And FB measurable function. And FB measurable function. Measurable function. We say that Fn converges to F. We say that Fn converges to means sequence Fn is just converges to F. Converges to F is measurable to is measurable to measurable is measure to or epsilon greater than 0, given epsilon greater than 0 and neta greater than 0 and neta greater than 0. T dash neta greater than 0. Greater than. There is a natural number n naught such that there is a natural number natural number natural number n naught such that n is greater than n naught is greater than n naught. The inequality mu a inequality mu mu of a equal to 0. So mu of inequality mu of a inequality inequality mu of a mu of a x is such that fnx minus f of x mod fnx minus f of x minus f of x greater than epsilon greater than epsilon. And less than neta. In other words, Fn converges to F is a measure for E such that limit n tends to infinity, limit n tends to infinity, limit n tends to 0, 0, mu of, mu of x such that mod fn x minus f of x, minus f of x, minus f of x, minus f of x greater than c, is greater than c, c equal to this. In this case, fn means fn, we write fn tends to f, means on x, means mean, measurable, measurable on x. Definition 2. Definition. The sequence of functions is said to be a sequence of functions, FNS functions, said to be a sequence of functions is said to be fundamental sequence with respect to a fundamental fundamental sequence fundamental sequence with respect to kind of convergence with respect to kind of convergence of convergence 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 if it is a Cauchy sequence, if it is a Cauchy sequence, Cauchy sequence, it is a Cauchy sequence. In this sense, for example, theorem 1 means Fn tends to F means in this case, Cauchy sequence. In this case, Fn tends to F means on X. Means on X. Theorem number 1. Based upon the definitions, we'll prove one theorem. Theorem 1. So that prove that suppose Fn is a Sequence of measurable functions. Suppose Fn is a sequence of sorry, Fn is a sequence of measurable functions measurable functions measurable functions measurable functions sequence of measurable functions sequence of measurable functions sequence of measurable functions and is a fundamental sequence fundamental sequence sequence fundamental sequence measure in measure fundamental sequence in measure. Then there is a measurable function f. Then there is a measurable functions. Measurable function measurable such that f st means such that fn tends to fn tends to f. This is miss. This situation is known as miss. Proof. Proof of theorem. Proof. Since fn is there, since fn is there, fundamental sequence in measure sequence in measure sequence in measure. measure to each integer I is greater than 0. To each integer I is greater than 0. Integer I is greater than 0. There is a natural number Ni. There is a natural number Ni. Natural number Ni. Such that for all M is greater than or equal to Ni. Such that for all M is greater than or equal to Ni. So N is greater than or equal to Ni. So mu of, that means mu of mu of mu of x such that fmx minus fnx mod fmx minus fnx x greater than or equal to 1 by 2 greater than or equal to 1 by 2i greater than or equal to 1 by 2i greater than or equal to 1 by 2i. So consider equation number 1. So we may assume that Ni equal to 1 to infinity. We may assume Ni I equal to 1 to infinity, I equal to 1 to infinity, is an increasing sequence of natural numbers. Is an increasing sequence of an increasing sequence of natural numbers. Increasing sequence of natural numbers. That is Ni plus 1. That is Ni plus 1 is greater than Ni is greater than Ni. I is greater than or equal to 1. Greater than or equal to. If Ei that equal to x such that fnix minus modulus of fnix minus fni plus 1 fni plus 1 I plus 1 x greater than or equal to 1 by 2i. 1 power 1 by 2 power I. Then it follows 1. Then it follows equation number 1. Equation number 1 follows equation number 1. That is MEAI, mu of EI, mu of EI less than 1 by 2 power I. Power I. I is greater than or equal to 1. I is greater than or equal to 1. X does not belong. If X does not belong to I equal to M to infinity, union of I equal to M to infinity, EI, EI. Mu of I, EI, EI. For R greater than S greater than M. For R greater than S greater than M. So we have mod Fn R modulus of Fn of X minus FNSX, FNS X, FNSX, X is less than or equal. Is less than or equal to sigma I equal to R plus 1 to R, I equal to S plus 1 to sigma 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 I equal to S plus 1 to R, I equal to S plus 1 to R. So modulus of NIX, modulus of NIX, modulus FNIX minus FNI plus 1x, FNI plus 1x plus 1ix is less than sigma I equal to S plus 1 to R, sigma I equal to S plus 1 to R, S 1 to R, 1 by 2i, 1 by 2i. It follows equation number 1. Okay. Less than uh, that equal to 1 by that equal to 1 by 2 power s. 2 power s. Equation number 2. Equation number 2. So that F1ix, so that F1ix, F1ix, F1ix is a Cauchy sequence for each is a Cauchy sequence. Cauchy sequence is a Cauchy sequence in X. Sequence in X for X does not belongs to X does not belongs to intersection M equal to I to infinity. Intersection M equal to I to infinity. That equal to union I equal to M to infinity EI that equal to A. That equal to A. Consider let but mu of A equal to but mu of A but mu of A equal to mu of intersection M equal to 1 to infinity. Intersection M equal to 1 to infinity. Union I equal to M to infinity EI is less than or equal to mu of union I equal to M to infinity EI for each M or M. That is less than or equal to 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 sigma I equal to 1 to infinity equal to M to infinity mu of EI mu of EI mu of EI mu of EI is less than sigma I equal to M to infinity M to infinity 1 by 2i that equal to 1 by 2 to the power of M minus 1 for each M for all M, showing mu of A equal to 0, showing mu of A equal to 0, mu of A equal to 0, mu of A equal to 0. mu of A equal to 0. Thus, Fni converges almost everywhere. Thus, Fni CGS. CGS means converges almost everywhere. AE means almost everywhere. Almost everywhere. To some measurable function. To some measurable functions. Measurable functions. Measurable functions. FNS means functions. FNS means functions. Say to F from 2. From 2. From 2. Shows that FNS is a sequence. Shows that. Shows that. Shows that. FNI is a sequence. Is a sequence. FNI is a sequence. A sequence. Sequence. Which is fundamental uniformly. Which is fundamentally fundamentally uniformly on the complement. Uniformly on the complement. On the complement. Uniformly fundamentally complement of the set of the set of the set union I equal to m to infinity to infinity ei for each m ei for all m. Therefore, Fni so ei for all m. Therefore, Fni tends to f. Therefore, Fni tends to f. Fni tends to f uniformly on the complement of uniformly the complement of uniformly the complement of u union I equal to 1 to infinity I equal to m to infinity ei and hence for epsilon greater than 0 for epsilon greater than 0 So mu of x is such that fni x minus fx modulus of fni x minus f of x greater than epsilon by 2 greater than epsilon by 2 epsilon by 2 tends to 0 tends to 0 as I tends to infinity as I tends to infinity. Equation number 3. Now since now since now since x is such that fnx minus f of x mod fnx minus f of x such that fnx minus f of x greater than epsilon by 2 greater than epsilon by 2 greater than epsilon by 2 greater than epsilon greater than epsilon subset of subset of subset of x such that fnx minus fnix minus fnix fnix greater than epsilon by 2 greater than epsilon by 2 union x such that x such that x such that mod fx minus fnix mod fnx minus fnix 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 greater than epsilon by 2 greater than epsilon by 2 we get mu mu x such that fnx minus f of x mod fnx minus f of x minus f of x greater than epsilon which is less than or equal to mu of x such that fnx minus fnix mod fnx minus fnix inx greater than epsilon by 2 greater than epsilon by 2 plus mu of x such that mod f of x minus fn x greater than epsilon by 2, greater than epsilon by 2. Here, since fn is a fundamental measure, the first term of right is arbitrarily small and also by 3, and second term is arbitrarily small. Hence, fn tends to f. Hence, fn is a fundamental measure. Fn is a fundamental measure. Fundamental measure. Fundamental measure. The first term on the right is the first term on the right. First term, right. Arbitrarily small, arbitrarily, arbitrarily small, arbitrarily small, and also by 3, and also by 3, means equation number 3, also by 3. The second term is arbitrarily small. Second term is arbitrarily small. Arbitrarily small. Arbitrarily small. Hence, Fn tends to F is MEAS, MEAS, is MEAS. So, theorem number 2. Your definition. Theorem number 2 and 3. Page number 85. Page number 85. Next, second part. Theorem number 2 and 3. 4 marks. So, almost uniform convergence. Page number 86. Definition. 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 Let Fn be a sequence of measurable functions. Let Fn be a sequence of measurable functions. Sequence of measurable functions. Sequence of measurable functions. And F be a measurable function. And F be a measurable function. F be a measurable function. we say that Fn tends to, we say that we say that we say that Fn tends to Fn tends to almost uniformly, yeah, almost uniformly, uniformly, almost uniformly, uniformly. If E is epsilon greater than 0, E is epsilon greater than 0, epsilon greater than 0. There is a set E, there is a there is a set E, there is a set E with mu of E equal, with mu of E less than epsilon, less than epsilon, and Fn tends to F, and Fn tends to F uniformly on X minus E, on X minus E, X minus E, uniformly X minus E, uniformly X minus E. In this case, we write, in this case, we write in this case we write in this case we write Fn tends to F, Fn tends to F, almost everywhere, AU, almost uniformly. AU means almost uniformly. So, short answer type question. Theorem. For 6 marks, most important. Theorem number 5. Theorem number 5. Statement. Suppose Fn is a sequence of measurable functions. Suppose Fn is a sequence of sequence of sequence of measurable function and function and F measurable function and F is a measurable function is a measurable function measurable function If Fn converges uniformly, CGS means convergence uniformly, uniformly to F almost everywhere, almost everywhere. Then, then Fn tends to F. Then show that, then converges uniformly to everywhere. Then show that Fn tends to F. Fn tends to F, tends to F. Almost uniformly. AU means almost uniformly. So proof. Proof. Fn converges uniformly. Uniformly. Just uniformly. To F. AE. Almost everywhere. Gives a set. See a set. Set. A with A with mu of A equal to 0. Mu of A equal to 0. And Fn tends to F. Fn tends to F. Fn tends to F. Fn tends to F. Uniformly on X minus A. Uniformly on X minus A. On X minus A. Therefore, any epsilon greater than 0, any epsilon greater than 0, epsilon greater than 0. The same set A is same set A is such that mu of A, mu of A, mu of A equal to 0. Mu of A, such that mu of A less than epsilon less than epsilon, mu of epsilon. And Fn tends to F uniformly. Fn tends to F uniformly. Uniformly on X minus A giving that Fn tends to F. Fn tends to F. So hence proof. Hence proof. Okay, we discussed it in this chapter. Hmm? On 10 marks theorem, 6 marks theorem, and concepts. Okay, now stop it. I'm leaving. Hmm? Thank you very much. No, this unit is completed. So next Saturday we'll discuss 19, start at 1920. Right? Thank you very much. Leaving.